Our talk this afternoon with Uzi Smilansky. He's going to tell us about random graphs and random matrices.
Yeah. The work which I'm going to report actually started a year and a half ago, in the Newton Institute program on graphs, where I met various luminaries in the theory of combinatorics and graphs. And I thought that it is a very nice idea to combine my way of looking at things, which is coming from quantum chaos, quantum graphs, and what they were interested in. And that resulted in some fruitful direction, about which I would like to tell you the last fruits. Now, it is not published, and I'm looking forward for comments, criticism, shouts that somebody else did it previously, telling me it's wrong. I'm all open to it. The work was done with my two youngest students, Idan Oren and Amit Godel. And to put it in as an introduction, I would like you to think always about these two pictures. This is a random graph, as you see. And then if you define some Laplacian on it, and you look at the spectrum of the Laplacian, and if your name is Jacobson, Mirlin, Rivin, and Rudnick, you do the nearest neighbor distribution, as we know and love to do. You get a function or a distribution which looks like the predictions of random matrix theory. When you see this and this, then you ask, how come? So my lecture will be to tell you a few initial directions, as a matter of fact, on the developing of tools, which are very common in quantum chaos and in quantum graphs, so that one can actually use our language and use our methods in this context, maybe learn a lot from combinatorics into spectral statistics, but maybe also go the other way and contribute something from what we know to the study of combinatorics on graphs. So to start at the start, we need a little bit of preliminaries. So I'm going to use graphs, which I consider as a set of V vertices connected by a set of E edges. The number of vertices will be capital V. The number of edges will be capital E. And everything is described in terms of the adjacency matrix A, which equals to G if I and J are vertices which are connected by G edges, and it is a symmetric matrix. And I need also at some point to speak about a neighborhood. So a neighborhood, R neighborhood, is all the vertices which are connected if you jump less than R jumps. I will speak about simple graphs, and these are the ones for which the Aij can be either 0 or 1. And then also I will avoid loops, self-connections. And then I will also talk about connected graphs. A degree is the number of edges which emanate from a vertex. And I shall speak about regular graphs in which all the degrees are equal. The number of edges for such graphs is equal to V times D over 2. This is exercise number 1. And from which we learn that for such graphs, we have to have capital V times D is an even number. Now, there are many ways to generate D-regular graphs on capital V vertices. And in the limit, when V goes to infinity, their number grows faster than exponential. And therefore, and this is an estimate which are given in combinatorics, I can give you the references. And therefore, it makes sense also to look at the V-regular graphs with a given fixed index D, fixed degree D, and make it a probability space which is discrete, and then I shall have uniform probability on all these graphs. And when I average over the graph on the GVED ensemble, that's what I'll mean. In passing, to those of you who remember quantum mechanics, H bar is 1 over capital V.
So are these, do you identify graphs up to isomorphism, or you do the counting? How are you doing it?
Probably after isomorphism. The graph is the same under cyclic permutations. Continue, we also speak only about directed edges. So a directed edge is a pair of connected vertices, and edge is going from I to j. And a little hat means that I'm looking at the reverse one, ji. It is convenient also to introduce the origin of an edge or its terminus. And E and T stand for origin and terminus, and E prime is connected to E if, of course, the terminus of E is the same as the origin of E prime. We can also introduce a very important matrix, which is capital B. It is in the space of 2E, which is the number of directed edges. And it tells you if E prime follows E. So it is the edge connectivity. We can speak about walks. A walk is a sequence of edges which are connected, one after the other. And we have to introduce the very important concept of non-backscattering. I think that Ofer called them non-backtracing, not non-tracking. Sorry?
Non-backtracking.
Non-backtracking. So this is the difference between the Rehovot dialect and the Haifa dialect. We call it. No, it's not. Okay, never mind. We come from different cities in Israel, so it must be a difference.
In Noga.
So we don't non-backscattering tracks are the ones which do not go back. And if I'm speaking about a T periodic walk, I mean that after T edges, I come back to the point where I started with. And I speak about trace T periodic walks, and it is quite easy to count them, and you can actually count them in two ways. Either you take trace of A to the T, the vertex connectivity, or you take trace of B to the T. Now, you can see already the connection. Trace of A to the T is what we know from spectral theory. So we have already spectral information here, and counting walks on the left-hand side. Walks, periodic orbits, T, A, spectra, trace of the spectrum. So this is the connection that I will all the time play with. It is very important also to count non-backscattering walks. And how do you do it? You introduce a matrix J which connects only between a pair of edges which backscatter to each other, and you subtract it from B. And if you do trace of B minus J to the T, you get then this number of non-backscattering walks. And this is such an important matrix that it even has a name. It's called the Hashimoto connectivity matrix. And I call it by Y. So this is the preliminaries. So now you know everything about graphs. Let us see what is known about the spectrum, or what is known about the Laplacian. So we have to define what is the Laplacian on such a graph. So the Laplacian is minus the adjacency matrix plus D times the unit. So it is a V times V matrix, symmetric, and therefore it has a real spectrum. Its largest eigenvalue can be shown to be just D, the degree. Remember, I'm speaking only about regular graphs. And then you can arrange the spectrum by decreasing order. And we are interested really in those eigenvalues which exclude the first one, the trivial one. Well, the question is, what will happen if we keep D, the topology, constant, and we go in the limit, the semi-classical limit, V goes to infinity. And then there is a theory by Kesten and Mackay, and they computed the limit distribution for this spectrum. And what they proved is that if you look at the distribution, first of all, has a finite support. It is supported on the integral from minus 2 square root of D minus 1 to plus 2 square root of D minus 1. And as a matter of fact, there is an explicit form for it. Here it is. If it were not for this guy, this would have looked exactly like the semicircle law. However, life is not so simple, and therefore there is a difference. And if you look at the numerics, and this is what done by the gentleman I mentioned their name before, and this was in the 90s, you have a very nice agreement between what you find numerically and this theorem. So this is proving a theorem numerically. No, this is a joke.
But you're giving all these graphs with fixed coordination number and fixed number of vertices equal weight.
Yes, that's what I said. That you give a uniform probability on this. Exactly. So this is the, I'm sorry?
What is D here? I mean, this is.
D is the, it is the degree.
And lambda is the parameter. Of the
Lambda is the spectral parameter.
Okay. And also, if you take one particular graph on it still looks like that, right? It's not just the average. Is it self-average?
This is averaged over this is average over cubic on
No, I
a
understand that this is the average.
yeah, but if you look, then typically it will look like that.
But
Yes.
still.
Yes. Right. Okay. Any question? Okay, then the four gentlemen, when they did the numerical experiment, they had to do what we call the unfolding of the spectrum, and this is, you call it, it's related to your clocking, is to find the clock which works like the Big Bang at constant intervals. So the S are the the clock, excuse me, and because we are unfolding it with the number function, the average number function derived by Kesten and Mackay, and I showed you before. And then indeed, when you do and this is standard job in any study of this kind, you get.
That's a local clock, right?
Yes, of course.
It's the local spacing.
Yes.
If it were a clock, this curve would just be a delta function at the distance.
Exactly. So this is but this is, of course, there are fluctuations here because the fluctuations are translated from the lambda to the S, and then this is why when you do the average, then you get this distribution. And Jacobson and Rudnick and their friends, they also did a detailed statistical test to see to what extent this is there is agreement within the statistical uncertainty between this curve, the GOE curve in this case, and what they find. And indeed, they use the Kolmogorov-Smirnov test, and they find that it is doing a very good job. So this is what I learned from being here in 2007 for half a year. You can also do a little bit to check what, to enhance, to look at the analogy a little further and follow various works in the past in which one can introduce some kind of a magnetic Laplacian or magnetic adjacency by associating with any connected vertex, bond, sorry, any pair of connected vertices, a phase e to the I phi ij. And so this is the new operator. If you take phi ji to be the negative of phi ij, you make this as a Hermitian matrix. The spectrum again is real. Time reversal is not obeyed. And lo and behold, if you repeat the calculation again with the Kesten-Mackay unfolding, you get a very nice agreement with GUE. At the same time, you can do the non-magnetic case, you get the same agreement. So there must be something true. You can do another statistical test in which you look at a different function. This is our beloved form factor. It is essentially a two-point correlation function. The Fourier transform of the two-point correlation function. Again, you use the unfolded variables. You compute this, you average. Here there is a missing G. And what you find numerically are these results. This function, this fluctuating function, is not self-averaging. So you need a large body of data to smooth it completely or do something else. But if you just take the raw data, averaging of a few hundred graphs, realizations, you get this function. And in one case, in the without magnetic flux, you see that it goes more close to the red line, and in the other one it goes more close to the blue line. This blue and red are GUE and GOE predictions. So again, numerical evidence points out to a certain connection, and the question is, what is the connection? And what I would like to convince you today is that the connection, or the, oops, does it run continuously? Or I pressed it so hard. Well, I ran out of battery because I pressed it once so hard that it doesn't release. Oh, now it released. Okay, so the real question, the title of this talk should have been actually counting statistics of cycles of periodic walks versus spectral statistics. And I would like to convince you that the statistics of the spectrum reflects the statistics in the counting of cycles in my ensemble, and vice versa. There is a dual relationship, counting statistics and spectral statistics. And the tool which I would like to introduce is the trace formula, which I will show you in detail. So what is the plan of the talk? I'll tell you again what I know. I think it is more or less what is known about counting cycles on d-regular graphs in the limit of large graphs. I'll speak about the spectrum and introduce Ramanujan. I'll speak in detail about the trace formula for the discrete graphs. I'll repeat a discussion of the Kestel-Mackay from a different point of view. And then I would like to show you that we can actually compute this function k of tau, which I showed you, the 4 factor, to leading order in its Taylor expansion near 0 and find the prediction of random matrix theory. I mean, the agreement with random matrix theory. So this is the first step that one can do in order to establish some agreement between the two theories. As I told you, this is only the first step in the discussion. I hope that I'll be able to fill up the time until by this very minute step.
So does this tell you about the level of repulsion then?
It is
level of repulsion?
it is related, not exactly, because this is, small time means large energy intervals.
Ah, okay.
So it is a long range.
And these gentlemen that showed you the picture just had numerics, had no theory?
No theory.
There is a replica-based theory for this.
I'm sorry?
There's a replica-based theory sort of for this.
I cannot hear, sorry.
There's a replica-based theory for this sort of thing.
Then you should tell me or take the and tell it.
Okay. Something from other countries.
But the replica is probably for something random.
Well, this is random. We have an
Graphs?
ensemble of graphs.
So for this graph, there is okay.
Well, then give me the reference and I'll save I save a few trees from Brazilian forest, then we don't have to print the paper.
It's not rigorous, but it's quite effective.
Okay, you will tell me afterwards, or in the comments. This is, you know, when I asked for comments, I didn't ask for such comments. Never mind, no, I'm very grateful. Now, where is the, no, I'm running too fast. So, what is known about counting, or what is known about the properties of d-regular graphs? The most important property of such graphs is that if capital V goes to infinity, and if you look at our neighborhoods of the size of the logarithm of capital V, then almost surely any neighborhood will look like a d-regular tree. And in other words, it means that there are non-backscattering periodic walks almost. Rare periodic walks are quite rare. If the length of the t is less than log v. If we denote by ct the number of t cycles, and when I say cycle, I mean primitive, so it doesn't repeat itself, non-backscatter, and also non-self-intersecting. T periodic orbits, and I count them modulo the number, which I mean where I start, and I don't count the direction in which they go, then there is a theorem which says that for such period t, this number Ct distribute as independent Poisson variables with a mean, when you average over the graph, which is equal to d minus 1 to the t over t, 2t. And this is a result which is due to, I think, to Bolobas and others. Now, having realized this property, essentially what Mackay and Kesten were doing to compute their formula, or Mackay was doing to compute the formula, was to compute the spectral statistics or spectral density for an infinite d-regular tree. And then, because we are interested in the limit of large V, then the resulting distribution can be used to describe the mean, the average density. I'll come back to it and I'll give you a different proof or different way of looking at it. Okay. Now, as I told you, the spectrum has the value d, which we don't care about, and the rest. And the rest, the graph is then called Ramanujan if all the rest of the spectrum lies within the support of the Mackay-Kesten, Kesten-Mackay distribution within these two. And one doesn't know if there are graphs of this kind, Ramanujan graphs or not. About 10 years ago, I think Lubotsky, Phillips, and Sarnak actually proved that such graphs do exist, and in particular, but only they could prove for the degree which is equal to prime minus 1. So there are such graphs. The rest is only a guesswork, numerical guesswork, what I'm going to tell you, and it's based on the paper, on the results which I got from papers which quote Khoury. And what he tells us is that a finite fraction of the graphs in G, V, D are Ramanujan. The fraction is approximately 2/3 independent of capital V or D. And if you look at the mean deviation of the largest non-D eigenvalue from the edge of the spectrum, then it behaves like V to the minus alpha. V, you remember, is the number of vertices, where alpha is approximately 0.6. You see here, this is the edge, this line is the edge. This is numerical experiment. This is inside the support, this is outside the support, and you see how the distributions get nearer and nearer to the edge. And then there is a conjecture, again, it is not proved, that the distribution can be described by the Tracy-Widom theory, which applies in random matrix theory for finite dimension. So what I would like to take home is that there is a certain scaling which tells you how fast the tail converges to the edge, and it is going like V to the minus alpha. Alpha is about 2/3. Okay, that is almost all the input. And now I would like to introduce to you Mr. Bartholdi. Mr. Bartholdi has derived a beautiful and very basic and very important identity connecting the two matrices which control the connectivity of the graph in the two languages. So suppose that S and W are any parameters, complex numbers that you wish to have, then this determinant of the unit in the directed edge space of the matrix S times B minus omega J. You remember J was the one which connects backscatter, is equal identically up to this factor to this determinant in which the adjacency matrix appears and the unit matrix appear with this particular combination of the constants. And it is very easy to prove it. It's an algebraic identity. So I don't want to spend the time on it, but it's really, you define a certain matrices, you multiply them, and you find out that their determinants are the same, and then lo and behold, you get this result. Very nice and very general, and I'll and this will be the basis of everything which I'm saying from now on. Everything is defined here. And what I'll do now, in particular, as an example, I'll take omega w, equals to 1. In that case, the operator which appears here will be the Hashimoto connectivity matrix, and then I will see what comes out. Well, then you derive out of the Bartholdi identity another important identity called the bus identity. And those of you who know the Ihara zeta function, the Ihara theory, it is based on this bus identity. So look at this. Change the variable from eta to 1 over from s to 1 over s, and lo and behold, you get that the characteristic polynomial of the Hashimoto connectivity matrix is related to this particular expression. Of course, we know already the trace of A of t is equal to trace of b to the t, so we know how to count t periodic walks. If we know the spectrum of y, we see that it is connected to the spectrum of A also. And therefore, we know that the spectrum of A can be used to count either type of periodic orbits, either with repetitions or without, with backscatter or without backscatter, but then also vice versa. And this is the reason of this duality between counting, trace of b to the t, and spectral information, trace to the A of A. And I repeat this, and I'll repeat it how do you say ad nauseam?
Nausea.
Ad nauseum, because I think this is the essence of everything that I'm saying.
You have a similar formula for counting systems. So maybe you compare them?
In a minute. It will jump at your face. So again, Mr. Bartholdi, let us calculate from here the spectrum of y. Spectrum of y is very easy. It has E minus V, which is essentially almost the rank of the graph, the number of loops, independent loops on the graph, minus 1. So there are plus 1 appears e to the minus v, minus 1 appears the same number of time, and then for every eigenvalue lambda of A, we'll find two eigenvalues, two values, which come out from solving this quadratic equation. We can write the solution explicitly in this way, and you see that if the graph is Ramanujan, then lambda L is less than 4d minus 1. Lambda L squared is always positive, and therefore these numbers will be a complex conjugate, and it is easy to prove that they will all sit on a circle with a radius d minus 1, the degree minus 1. There will be two יוצאים מן הכלל. שמואל, יוצא מן הכלל? Exceptions. If you take lambda 0 equals to d, the simple eigenvalue, one of them, then the eta 0 plus minus will be 1 and d minus 1. And therefore, if you collect all this together and assume that the graphs that you are talking about are now Ramanujan, then I can write that the number of t-periodic non-backscattering walks, trace of y to the t, is equal. The largest eigenvalue is d minus 1 to the t. There is a correction which comes from the plus minus eigenvalues, and then there is the fluctuating correction which comes from the non-trivial eigenvalues of the adjacency. Remembering that the Chebyshev polynomials are defined in this particular way, t of n of x is cosinus n or cosinus x, the first kind of Chebyshev polynomials, I should say, then I can write the trace of y of t is equal to all this plus a sum over the spectrum of A, in which the argument is the spectral parameter, spectral eigenvalue, divided by the 2d square root of d minus 1. So I just copy it once again, and what we see here is that the number of t-periodic non-backscatter walks is equal, mostly increases like d minus 1 to the t, and that is quite natural because you cannot go backwards, so you have to also to go forward, and d minus 1 to the t is the simplest counting of such a walk. There is a fluctuating term, there is a systematic odd-even staggering. So when t is equal to 0, we have this term is active. When t is not is equal, when t is even, this is positive. When t is odd, this term doesn't contribute. So we have an odd-even effect, fluctuations, and we have this kind of a fluctuating term, which contains the information about the graph. On average, it behaves like v to the d minus 1 to t, the variance of it. So it is natural to define this object, little y of t, and it is equal to trace of y to the t minus d minus 1 to the t, and this is something which you expect to be the mean value of trace y to the t, which is actually a theorem for small t by Bolobas, Mackay, and Wormland. And for large t, it is also quite easy to see because this is the dominant term. So you reduce and you define, you somehow normalize it conveniently by d minus 1 to the t over 2, remembering this effect. And this is the information that you would like to take from counting non-backscattering walks. We count them, we subtract the mean, we divide by some kind of a mean fluctuation, and we get this expression. And again, if we average over G, over the ensemble, we expect this to vanish, at least for small t and for very large t, and then the rest should give us the information about whatever we are interested to look at. So here it is again. This is the result which I have written. And now you do a very simple exercise. You multiply by the Chebyshev polynomial of lambda over 2 square root of d minus 1. This is the weight to make it normalized. You sum over the t. You remember that this sum is related to a delta function, which is weighted by the proper weight of the first Chebyshev polynomials. You do a little bit more tricks. You make a few more observations, because trace of y to the 0 is just 2e. Trace of y1 is essentially 0. There are no periodic structures of period 1. There are no periodic structure without backscattering of order 2, so you have to remember also them. And after doing a little bit of work, you get Shmuel a trace formula. So where do you get the parts from? This is just from what I told you before, that you get a delta function when you take this product of t to t, the Chebyshev polynomials at 2 values. So this is just coming from the essentially orthonormality of the Chebyshevs. This is just a correction which is of order 1 of capital V that I don't want to consider in the continuation, but I can compute. The interesting and the most surprising part for me was that if you take this creature, the plus minus one, you remember the one which makes which distinguishes between odd and even graphs. You add to it some numbers which you have left out from this summation, you get the Kirsten-Mackay formula. And the rest is just a sum over the periodic walks without backscatter from 3 to infinity. These are 3 is the shortest non-backscattering walks. And this looks exactly of the form of a trace formula. There is a smooth part. Everything is defined for lambda less than 2 square root d minus 1. So this is the smooth Kirsten-Mackay form. This is sum over periodic orbits. We have, you can think of lambda over 2 square root of d minus 1 as the action per step. Each step we acquire.
Do not independently in some
Sorry?
way? This is the action per step.
That is how, I mean, this is an interpretation, you see. It appears it appears.
Only from there you know it. Because in the Gutzwiller formula, there is a classical analog and so.
Look, this is what T times lambda, so this you can interpret as the contribution per step.
Is there something like the Maslow's index?
No, come on. There is no dynamics here. But you see, to some extent, okay, let's forget about it. But this is the trace formula. Again and again and again. Spectral information, mean spectral information, information about periodic orbits. Yes, Uzi.
Sure about the meaning.
Sorry?
Just to be sure about the meaning of this formula. So this is not yet average.
No, no.
For a particular,
Ramanujan graph.
then this is a continuous function. On the left side is not continuous. It's the sum of the routes.
Yeah, you see, you have this is also not a continuous function. Rho of lambda is the sum of delta functions. Here it is. So you can write the sum of a delta function is equal to something smooth, not really smooth with edges, and something which doesn't converge. You have to think of it in terms of no, look, Uzi, not Uzi, Ofer, I'll explain to you. You have to think of it. You have to think of it as an equation of distributions, and then everything is okay. You can also think of it in a different way. You can always sum up to a finite number of n. Then you get a density which is spread, which is smoothed up to 1 over capital N, and then you equate functions because this will be a finite sum, this will be a smooth function, and this will be also a sum of Lorentzians or something.
What plays the role of the Lyapunov exponent?
There is Shmuel. There is no. The dynamics here is quite. It is the form which matters, and you see, there is something, but But you see, it is very surprising that things appear in this way because I avoided from the very beginning the treatment of backscattering. In my periodic orbits, there are no trees. Yet, the Mackay-Kirsten appears here, even though I did not mention in all the derivation a tree even once. You see, it pops out of the blue. I don't understand it, but it is, I mean, numerically, mathematically, I hope it is correct. I mean, arithmetically correct. Spectral statistics. We can, again, express this, I can invert this relationship. Rho tilde is the difference between rho and the mean distribution. Rho tilde is therefore related to you remember, this was the change in the number, the deviation from the mean value of the number of T periodic non-backscatter walks. And if I take this absolute value, if I square this and the average over G, I can write this equation, and here I'm cheating a little bit because I average over the entire G. whereas I believe that everything will eventually look like Ramanujan. You remember capital V, when capital V goes to infinity, the Ramanujan spectrum becomes smaller and smaller. So I'll show you that I have a remedy for it, and I'll show the remedy. But let us assume first that all the graphs are Ramanujan. And then what I see here is the two-point correlation function of the spectral density. Rho at U, rho at V, average over G. This is the weight. And if I make a variable, change of variable from the interval of the support of rho to the circle, actually to half circle, then I introduce a new parameter, phi, and then I see that this equation is the two-point correlation function for points of the circle, for the spectrum of the circle, is related to yt squared average. And the only difficulty here is that the function f, the spectrum phi, is still unfolded, because I took a spectrum which had a non-constant density. This was the spectrum of the adjacency. I transplanted it into I transferred it, I mapped it onto the circle. So I still have a spectrum which is not yet folded. It's unfolded. The intervals between the successive phis.
The Jacobian from the change of phi.
This is just a transformation.
But du is from d phi.
No.
Du is not d phi. What happened to the?
I just define a new variable. Phi is equal to r cosinus of u. Phi is defined on the unit circle. That's it. And I just look for every u. U is lambda over square.
Du and a dv.
Right.
I'm wondering about.
Yeah. You see, u. I made a little. I didn't explain that u and v are the spectrum divided by 2 square root of d minus 1. So I took the spectrum, I quetched it, I quetched it without changing the density. I just quetched it. And once I did it, I could now go over to the circle, and I have it on the circle. It is still not equally spaced on average. But if I continue, I can even write it. This is just copying, and then if the phi k were equally distributed, then this is nothing else than the form factor for the corresponding spectrum. Unfortunately, it is still a not unfolded sequence, and therefore I have to do a little bit more work to get it. But until this particular point, I see that my counting information is directly related to the form factor, yet unfolded, but I know how to unfold it, because I know what should be the density of the u's and v's, because I know the Mackay, and I know also how to make the next transformation. So the unfolding is done by defining a new variable, which is nothing else than the unfolded, this S is the unfolding function, and then if I do the computation, I find that this K is equal to a convolution of the proper information, the proper two-point form factor with this argument integrated over all the eta. And if I take tau to 0, I see that tau is nothing else than t over 2v minus 1. If I take tau to 0, I can prove that k tilde of t, if t is computed in this way, goes to kv of tau. So if I have anything to say about k tilde at short times, I can say something about the proper. I can compare this to random matrix theory, because this is already written in a form that random matrix theory loves. And indeed, just taking the definition of this y and remembering what I told you before about the Poisson distribution of these numbers, I can easily show that the average of this quantity is equal to 0, to 1, because the Poissonian character tells, of this distribution tells me that the variance and the mean are the same. And this is for Poisson. And therefore, this triangular brackets is equal to 1. And therefore, out of this, I get immediately the result that k of v of t, which is k of tau. So I got already the universality in the sense that I don't have independent variables t and capital V, but always the ratio of t and v come into play, is equal to 2 tau for t tau equals to going to 0. And this is exactly what random matrix theory tells us. And this is a proof. I can repeat the same computation. I don't want to go into it for the magnetic case. And I can get the same number, the same kind of agreement. And numerically, if you do the work, these are the not unfolded distributions. So this relates directly to counting of periodic walks. And you see that this is the folded, this is our expression, and it fits very well the data, which is not a proof, but it shows that we are doing somewhat, we don't do something completely absurd. Now,
So with the magnetic case, GUE?
GUE.
GUE.
There is the tau. It goes like tau, not like 2 tau. This is the GUE. This is the pure GUE. This is folding it in the proper way. If you take GUE and fold it in this way with the known S from the Keston-Mackay expression, you get this function, and this is the data.
What does it about? Why is it not GUE?
Because it is not, because you have to look at it for an unevenly distributed spectrum. Okay, let me just mention how one can avoid the problem with Ramanujan. This is again Bernoulli. Take W not equal to 0. Take any number between 1 and d minus 1. And look at this y. Now I allow, if I take trace of y omega, I allow now backscatter paths with a certain weight, which is 1 minus omega. But who cares? I can do it. And then if I look at, I can derive this all the same result as before. And again, I get a function. I wrote it rho of lambda and omega, but this is not a function of omega at all. It is the spectral density. It's the same spectral density. It's the spectral density in the same way. However, I have here a different smooth part whose support is not anymore 2 square root of d minus 1, but 2 square root of omega times d minus omega, which is larger than d minus 1. So I can increase the support as much as I want and put all the spectrum inside. And a trace formula, but now, lo and behold, the YT count also backscatter parts with a weight omega, 1 minus omega. So what do? I gain by by enhancing the domain of the spectrum, which I can treat by a trace formula. I lose by adding many more periodic orbits. But this is an identity again. So you see there is what do you call it? A continuum of trace formulae. And they only differ by the way of the partial summation that you are doing here versus here, because the result is the same. So if you did proper partial resummation, you will transfer out of this that part, which will turn this into a Ramanujan, into the previous case. And of course, if now I want to go to the limit capital V going to infinity, then I will take omega of the order 1 plus constant times V minus alpha, and then I'll be able to do the job. The Chairman shuffles in his place, so I should stop. I don't want to speak about this. Those of you who know Hebrew can read what is written here. And instead of the summary, I tell you what I think one should do in the next, and this is what we are doing now. is to compute the next order corrections to this counting, because the formula is correct anywhere. The only problem is that now counting becomes more complicated because we don't have the simple Poissonian character of periodic of these cycles, but one can do it in a systematic way. And this is one important thing which we have to do. And the other one is to translate what we know from this random matrix expansion and random matrix maybe ansatz, and to come back to the combinatorial people and tell them, look, this is what must happen. Can you perhaps sharpen your tools and prove this? So I ask you, can you? We can. Right? Okay. Thank you. I screwed up this.
Well, I was having trouble with
Sorry?
I was having trouble with it too.
Let me finish with it completely. So, other questions?
Destroy it completely.
Lose the battery.
No, it's the little knob.
It's
is-
gotten stuck. Well, don't worry about it.
Okay, I don't have any questions, so I can play. No, it's
some questions. There are questions here. So.
Yes.
How is it that you started out with the theory that you were just counting loops and things, and pretty soon you came to this formula that was all in terms of non-backscattering loops.
Mhm.
How is it that it turned into a theory that really just cares about backscattering?
Which includes. Thanks, Anna.
No, I think I thought I had the impression that you ended up talking about an operator that.
Yeah, B minus. You see, there was a B minus omega J. When omega equal to 1, it cancels exactly the backscattering part which is in B.
Yeah.
When omega is not there, then it leaves the possibility to do backscattering roots, but with a weight which is 1 minus omega.
Right. So I mean, physically, or what's the intuition?
There is no physics, I think. No, you see, it is all. You see, it is not. It's not. It is resummation, because I can even write you. You see, I wrote when I was.
This Bartolio is just a clever reasoning.
It is a clever resummation. You see, it is comparing determinants of in different spaces. And as a matter of fact, the surprise is even bigger. When I was here and I started to think about it, I invented something which is called a unitary evolution operator on graphs, on discrete graphs, which is a unitary matrix. And I obtained a trace formula starting from this unitary matrix. And then I did not even have something like which looks like a Kirsten-Mackay distribution, but the smooth part was, hold tight, it was a Lorentzian. Now I thought, how can it be? How can I get a smooth part which is a Lorentzian? So I looked at the other side and I saw that if I sum up exactly those periodic orbits which are of order 2 and transfer it to the other side, then instead of having a function which decays for large spectral parameter like 1 over lambda squared, the 1 over lambda squared disappears, is cancelled, it's a resummation, and I get something which decays like 1 over lambda to the 4th. To do the 1 over lambda to the 4th requires much more work. I didn't know how to do it. So all this work which I'm telling you comes because I was trying to understand where do I have the freedom of interplaying between what I would call a fluctuating part which doesn't fluctuate because it has smooth parts, and those which are the proper mean, the form distribution, which is not only what you get from the trace formula, but also what you get if you average over the entire ensemble. It has the advantage. So it is the ensemble average, and not only the term which you get for each particular graph. So this is all. This is a surprise to me. I didn't see it at least in quantum chaos. I didn't see an analog of it in other trace formula, which I know. Yes.
Doing this has a very
Eigenfunction statistics.
eigenfunction.
This is the work of Jonathan. Talk with him.
Second question. What about speculating on mixed graphs, like random graphs with non-random parameters?
Sorry?
random graphs with non-random components?
What do you mean?
I mean, I don't know.
Look, I define an ensemble. It is a well-defined ensemble. There are ways to construct it, and that's where I'm working. So it includes all of them. I don't know what you mean non-random. Is three?
Like,
Is
yeah,
three?
random
Is the number
can
3
be-
random?
Right.
I don't know. Yes.
The result for the leading term correspond to a diagonal approximation.
It is exactly the diagonal approximation. It is, you see, because diagonal approximation in quantum chaos means that our actions are independent. And this is exactly it. And our counting probably is an analog of your counting of actions. That's what we are now doing. And Berkolaiko lends tonight.
Because I mean, I would imagine that off-diagonal, I mean, there are some off-diagonal pairs which still have identical actions.
Yes, because you see, all the identical actions are there, but it is the counting of them. And there are corrections because of counting. You see, the non-backscatter are cycles only for small t. And then you have to add the 8 figures and the double 8 figures and all the zoo that you know and love. Yes.
Random graphs were also studied in quantum gravity, where they make some genus expansion. Can you obtain similar formulas specifying a particular genus for your graph? I mean, some relation between number of edges and vertices.
I don't think so. No, I don't. First, let me say I don't know. I escape easily. No, I don't know. You see, these graphs are so idiotic. Quantum graphs at least have length, so they have metric. So the spectrum is infinite, and you have a metric. You have a Schrödinger operator. Continuous.
These graphs I'm talking about in matrix models do not have any
So I
length
don't know.
length scale.
I don't know. No, I don't know it. This is the most elementary, most simple Laplacian that you can think about.
Well, what is the what do you imagine the implication to be for combinatorial? What kind of questions do you think this thing could
You see,
answer?
the question, the counting of non-backscattering works. So I can tell you, that if you count the non-backscattering works of length t,
Yes.
when t is larger than capital V, then
Is larger than
if the period
Yes.
is larger than the size of the graph,
Mm.
then, or when I look at t over capital V goes to a number larger than 1 when capital V goes to infinity, then I expect this number to decay like 1 over, normalized as I normalize it, will decay like 1 over this parameter, t over V. No, because the k of t becomes 1, and there's a factor of t in front, so it's 1 over.
So
This is a result which is a combinatorial. Must be defined.
Is that known in the combinatorial literature or not?
Noga alone. I asked Noga.
Noga.
I didn't speak with Noga. He was in Princeton.
Any other questions or comments?